So we're kind of extending the topic from the last video, which looked at giant covalent structures. And fullerenes are types of giant covalent structures, much like diamonds, graphite, and graphene, and they're also made up of carbon. What makes these structures unique is that they tend to be hollow in some way. In the case of Buckminster fullerenes, a hollow ball, essentially. But fullerenes, or rather the Buckminster fullerene, was the first fullerene to be discovered. The molecular formula, or the most common molecular formula, is C60, as in this hollow sphere is made up of 60 carbon atoms, and there are actually a mix of different shapes on its surface area. 20 hexagons like this one, and 12 pentagons like this one. It's a pretty stable molecule, and this means that it doesn't react or decompose too easily, and to the naked eye it has the appearance of black and brown crystals. It's also quite soft as well. Its structure actually allows for certain uses, in particular uses in medicine and industry. So for medicine, certain substances or drugs could be contained inside the ball, because that's essentially what it is. It's a sphere, and the ball can then be used to deliver this drug to the body, probably in a situation where it can't be swallowed or injected by itself too easily. And for industry, this particular fullerene has a large surface area. And this means it can be used as a catalyst, which is something we use to speed up the rate of a reaction. Now, you don't need to know really what this is, any more detail about catalysis, but this is what we could use it for, at least in theory. Right, surface area SA for short. And actually, on that note, there are even larger fullerenes that have been manufactured since, such as ones that have formulas of C70, so are made up of 70 carbon atoms and have even larger surface areas. If we go to nanotubes, which, as the name suggests, are essentially hollow cylindrical tubes, the carbon atoms arrange themselves in hexagonal shapes in this case. And something to be said about nanotubes is that the ratio between the length and diameter is very high. This basically means that the length of the tube is massive, so distance from here to here is massive compared to the distance from one side of the tube to the other through the center, like this. So they're basically very long and skinny. Nanotubes can be used as conductors of electricity and heat, as well as for uses potentially in medicine and industry. A particularly good use for nanotubes could be for things like tennis rackets and other related pieces of equipment. They are strong materials, nanotubes that is, are strong materials which provide strength without adding too much weight. This is because these nanotubes have a very high tensile strength. And tensile strength essentially means they're very difficult to break through stretching. So that's all for fullerenes. We're now moving on to something slightly different, which is polymers. And polymers are molecules which are formed when many smaller identical molecules are bonded together to form long chains. So these smaller molecules which make up the polymer are referred to as monomers. By far the most common example given is ethane, which is exactly what these molecules are. These monomers, which are all the same, bond covalently to each other to form this thing called a polymer. The atoms shown here is a section of a polymer where 4 ethenes have combined. But for most polymers like this, they're usually made up of more than 4 monomers. So in that case, drawing out the whole molecule, which is likely made up of hundreds or thousands of these ethenes, isn't really very practical. Instead, what we can do is we can put ethene into a bracket and use the value of n here to determine how many of these monomers will make up the polymer. So in this case, to the right here, if there were only 4 ethenes making up this polymer, then the value of n would be 4.